sing.
Hello, everybody. Welcome to this session on matching database to the workload. My name is Rick Houlihan. I am a senior practice manager for database services at AWS. I focus mostly on NoSQL. And over the last several years, I have migrated well over 1,000 workloads across hundreds of customers to AWS across a variety of database platforms, not just NoSQL. So I'm kind of rather uniquely qualified, I think, to talk a little bit about this subject. How do we push or choose the right database for the workload? That's a typical day in my life, is really what I end up doing on a repeated basis. So from this conversation today, we'll talk a little bit about the types of workload classifications. Now, how many people were in Sean's session earlier? Okay, so quite a few. When Sean talks a lot about the purpose of an application, and really what applications are very complex beasts, right? They're not just one thing. Typically multiple services make up an application, and multiple workloads make up an application. So a lot of the graphs that Sean was bringing up, we're talking about complex applications that are built up from many services, that are made up from many workloads. And we'll talk about how to classify those workloads and what we kind of go through the dimensions of a workload that we look at when we try to classify these workloads and look at what would be an appropriate database for a particular workload. We'll get into some of the traditional approaches to scaling, typically with relational databases, because we all kind of understand this, right? And again, going back to Sean's session where we talked about, back in the 70s and the 80s, right, we had 3 databases. They were all relational platforms. And that's kind of what we did everything with. And so scale is a big dimension of workload, right? When we start looking at workloads and we start looking at what kind of database am I going to use, for a given workload, scale is an important dimension. And how we used to scale and how we dealt with scale with relational compared to NoSQL databases, which is kind of the next generation of solutions that we have, and there's a variety of those. And we'll talk about how they compare and why they may scale in a little bit differently, a little bit better than the relational database. And then we'll talk a little bit about the flavors of NoSQL and some of the differences between NoSQL and SQL and why we're even looking at all these different solutions, right? I mean, we have all, as Sean said, over 300 database platforms being tracked today, a variety of solutions that we never really had to consider before that are purpose-built for many, many reasons. And so kind of deciphering, what is the purpose of this workload, really, and why does this database fit is really what we're going to get into in this session. So when I talk to teams, customers, and I deal a lot with internal teams at Amazon, and a lot of the times I'll ask the question of why did you choose this database that we're using, that we're building around? And typically I get one of these 3 answers, right? Because we heard it's cool is really what I get a lot. Which is not a great answer, right? You don't want to use a database because it's a cool thing. You want to use a database because it's the right thing, okay? Because we have a site license, because we already own this technology, so we're going to do everything with this technology because we own it already. And that might seem like a frugal investment, but the reality is most of the time it's not the best decision, and we could probably do things better with solutions that are built for that. And then, of course, there's always the, hey, because I know how to use it. Right, so because the skill set is commoditized or because the skill set is something that's generally available in my organization, we'll use this database. But the best reason to use a database is this reason, right? Because the database is purpose-built for what my application is really designed for, okay? And that's what we're going to get into today. What does that mean when I talk about what is my application designed for? Again, we have lots of different workloads that make up a given application today. So when we get into that, we'll talk about what are the types of workloads, right, that we can run into when we're looking at database solutions today. So there's a kind of I guess you'd say, messaging that's being adopted in the industry across the analysts to say that we have kind of 2 types of workloads or 2 types of applications. There's an operations-focused app and there's an analytics-focused app. And the reality is, it's not so clean cut. But typically, if you look at what's generally been in the realm of the operations side of the fence is what we would call OLTP apps, okay? Online transaction processing. These are applications that are they represent a regular business process. Something that's repeatable. It happens the same way every time. So when the transaction is executed through the system, whether it's an order processing application or some sort of reporting application or something that requires human interaction or not, it's a very regular process that the application has to go through to process that data. And this is the most common type of application, right? Regular business processes come in many shapes and sizes, and we build applications to handle these processes, and that is definitely the most common application type that we run into. When we get into the analytics side, we start looking at more kind of BI reporting solutions, ad hoc queries and access patterns that are not necessarily well understood, right? They might not be the same all the time. The questions I'm asking of the database are going to be different depending on the user, depending on the day, depending on the nature of the workload that's executing. Now, you might argue that some operational or online analytics applications are actually operationally focused, and I wouldn't disagree with you. This is where we start to get into maybe this line isn't quite so clean and there's a gray zone there, but the reality is OLAP workloads typically provide some sort of an aggregation, an ad hoc aggregation, or something that's not a predictable and repeatable process. That's what an OLAP application would support. The third type of application we'll talk about, a workload, is really a decision support system. Right? These are kind of long-running queries. You think data lakes. You're asking questions of a large pool of data, and you're trying to drive decisions around how you're going to run your business. Right? So this would be looking at maybe how efficient your organization was in consuming resources for a given project, and feeding that information back up into the management process to determine whether or not, what kind of decisions you want to make in governing your business. So typically these types of workloads are the things we're dealing with, OLTP, OLAP, DSS, and they break down in those categories of operations focused, analytics focused, and they have characteristics, right? Repeatable process, something that is, I know which way the data is going to be processed every single time it runs a transaction. An ad hoc process where I don't necessarily understand the access patterns that are going to be coming in, they're going to be asked of the data when this application is running. And then, of course, the long-running queries where I'm asking questions of big chunks of data. And these are typically where we start to look at breaking down our workloads. So what it comes down to when we look at any one of these workloads, right, we have types, we have kind of a pattern flexibility thing here, right? Is it a repeatable process that I can, with well understood access patterns, or is it not, right? And how big is the workload? And so scale is a huge dimension of trying to determine what is the purpose of my workload, right? And problems with limited scope are pretty easy to solve, right? If I have a need to manage the inventory in my store, for example, that might not necessarily be a huge amount of data that I need to manage. As a matter of fact, I might have a point of sale system at the cashier that has all of the data that I need to run my whole store right in it, right? And that's fine for me as an individual store owner. That's all I need. Now, let's say I want to build a system that's designed, to do root cause analysis for, to correlate transaction level events. And we actually worked with the company who was doing this across global markets, right? And that's a massive workload that's totally different. I can't run that on my laptop, right? I'm going to need a totally different database and a totally different processing infrastructure to run that application, obviously. So when it comes down to it, it's really about understanding the scale of your application, right? So we have a couple of dimensions there. We have the flexibility of the access patterns that I'm trying to support. Are they well understood or are they not? I have a scale issue and dimension that I'm looking at here. How big is this application workload going to be? And these are definitely things that are going to affect my database. And when we get into looking at sizing, the database, it's not easy, right, to do this. And typically what you end up doing is over time, as the application starts to scale, you're going to increase capacity in chunks. Right? It's kind of a step function. And when you overlay the demand for your application over time, you end up with a situation that looks something like this, right? Where I'm either going to be over-provisioned or I'm going to be under-provisioned. And when I'm over-provisioned, I'm wasting money. When I'm under-provisioned, I have a bad customer experience. And there's this brief moment in time where that line crosses where, oh, I'm perfectly provisioned, right? So this is not an easy exercise, and typically the way that we've gone about doing this in the past is to look at scaling the relational database, because it's been the only choice we've had, and relational databases don't scale easily, right? They typically scale vertically. What that means is I'm going to start off with a certain size of infrastructure to support my application. The demand for my application is going to increase over time. I'm going to have to increase the size of that box, right? Because that's how you scale a relational database. You get a bigger box. And eventually I'm going to increase the capacity or the demand for my application beyond the capacity of that box, and I'm going to need to get a bigger box. And this is a never-ending battle. I mean, I've been dealing with this for decades. We all have, right? It's sooner or later you run to the limit of what you can deploy as far as physical infrastructure to support a single instance of your database. And we hit that point, at Amazon, and it's why we wrote the DynamoDB white paper. But eventually what's going to happen is you're going to start saying, okay, I'm actually bigger than a single instance, and we're going to get into this trying to partition the data. And this is actually, even my career, this is how I ended up getting into NoSQL technology. I worked in the ITSM space. The event load for enterprise IT infrastructure is an amazing amount of data that you're processing, and we ended up having to do this time-based partitioning of the event streams coming in from hundreds of thousands of devices deployed on some of the largest enterprise IT infrastructures out there, and it becomes a logistical nightmare to try and manage the data this way. So eventually what we started looking at was alternative solutions, and what we stumbled on at the time, this is about 10 years ago, was NoSQL databases, right, which were designed specifically to solve this problem of scale, right, to get past this, having to get a bigger box all the time. And the way they did that was that they support a de-normalized data model, and they couple that with sharding, and they can do this to provide horizontal scale and nearly unbounded throughput and storage, right? So almost nearly, for all practical purposes, you could say infinite scale, right? There's no practical limit to what you can do with a NoSQL database. And the way they do this is interesting. Now, with relational databases, when you start to distribute the data across multiple shards, you can't really join that data so easily. So the whole ad hoc query pattern and normalized data model breaks down when I start to break across partitions. So when we go into the NoSQL type of model, what we're really doing is we're trying to take all these items that are coming into the tables in a de-normalized structure, and every one of these items is going to have a mandatory attribute. In DynamoDB's case, it's called a partition key. Okay? All NoSQL databases have an equivalent. In MongoDB, it's a shard key. They call it a partition key in Cassandra. But what you're doing with this attribute that all items must have is you're laying out these items in what DynamoDB does is an unordered hash index. So we will hash the attribute. So in this case, let's say we have a bunch of items coming in. These items have an ID attribute. This is the partition key. We will hash the ID attribute. We will lay these items out across an unordered index. And the reason we're going to do this is because now when I want to scale, all I have to do is chop up that key space and distribute those items across multiple physical nodes. Okay? So now when I go get data, I'm going to provide a partition key value that's going to direct the system right to the exact storage node where that data lives. This is how NoSQL databases become fast and consistent at any scale. Right? I'm providing that key value access pattern that's driving me right to the exact place I need to go to get the data I need. Now, DynamoDB does a couple other things on top of that. We're not really going to get into design patterns in Dynamo, but it's important to understand how NoSQL databases scale and the decisions that we're making when we scale. Okay? So if we look at data in general, and if you're familiar with product management, there's this thing called the iron triangle of product management, right? You can get things good, fast, or cheap. Pick two. Right? You're not going to get all three. Data has its own iron triangle. It's called CAP, right? And CAP is about consistency, availability, and partition tolerance. And you're going to get two of those dimensions. And NoSQL databases make a choice of how they apply the CAP theorem. So if you look at the three dimensions, we'll talk about consistency first. Consistency is about clients being able to see the data the same way. All clients of the system that are connected to the system will be able to see the same data when they read and access the database. Availability means that all clients who are connected to the system will always be able to read and write. And that's important, both dimensions. Read and write. If I can read the data but I can't write, then the system is not available. Okay? So there's consistency and availability. And then there's partition tolerance. That's when we start to scale out the system, right? We start to partition the data store. Will the system operate well when a physical network partition is introduced and these nodes stop communicating with each other? So NoSQL databases make a choice when they break that consistency and availability. Relational databases will, relational databases will always, what's going on? I'm missing it. Okay, yeah. Relational databases choose to be consistent and available. They ignore partition tolerance. This is why they scale vertically. I always have to get a bigger box because they don't partition. When a relational database fails over, or when relational database clients will always read the same data, okay? And it will always be available. All clients that are connected to the relational database will always be able to read and write when that database is online, okay? When a partition exists between the primary and secondary, the database actually goes offline. So when the data is online, it's always available. Now, NoSQL databases make a choice. They can either be consistent and partition tolerant, like many NoSQL databases are. MongoDB and DynamoDB, for example. DynamoDB is a consistent database. Within the region, if I write to DynamoDB and I request a consistent read, I will get the same data back that I read. Other databases NoSQL databases choose availability, right? Any node can take a write, anything. So if a network partition exists between in a CP system, the primary is going to stop taking the writes until a new primary steps up and takes over. All writes will occur at the primary node, okay? In an AP system, that's not the case. All nodes can take a write. So if a network partition is injected into the system, any node on either side of that partition is going to continue to take writes, and at some point when they start talking to each other again, it'll resolve the conflicts, okay? There's callback functions and there's mechanisms to be able to do this in most databases that act in the AP manner. Now, DynamoDB is the only database that acts as both. Regionally, within a region, we're CP. With global tables across multiple regions, we are the only fully managed master-master, globally replicated NoSQL database, and that gives us that AP kind of function. Right? I can write to any table in a global table replication loop, and those writes will eventually replicate and deconflict themselves based on timestamp. So DynamoDB provides both CP and AP functionality. So these are the kind of choices we're making when we decide to go with a NoSQL technology, right? Relational, we're going to scale vertically. That's going to give us some limited scalability, but it's going to give us a lot of pattern flexibility because I can support ad hoc queries. Now, NoSQL, I'm going to scale horizontally. It's going to give me a lot of scalability. It's going to give me a lot of efficiency, but it's not going to give me a lot of flexibility in how I access the data, right? Because it's de-normalized data structures that are really designed to support the access patterns. Okay, so now we're starting to get to the points here. We have a pattern flexibility dimension, right? How can do I know what it is that I'm dealing with when I run my transaction, right? Is it a well-understood access pattern? We have a scalability dimension, right? And we have this efficiency dimension. How long does it take things in the system to occur? So before we get into talking about your database options, there's one thing a point I want to make, and it's really important when you start looking at new technology. Now, relational technology has been around for decades. We all understand these things. When we interview developers today, we don't ask them what's an inner join, right? Everyone kind of knows what an inner join is, right? But 30 years ago, we did have to ask developers that because most developers, when they created a relational database, they didn't understand relational technologies, and they would build big, giant tables that looked like Excel spreadsheets, okay? And that was a very common thing people did. It was a terrible anti-pattern that people did, decades ago. And so what this chart really talks about is when people, on the bottom, we have this kind of technology adoption curve, right? And there's going to be some sort of technology trigger that's driving innovators to deliver new solutions. In database technology, it's really about what I call data pressure, which is the ability of the system to process the amount of data that it's being asked to process in a reasonable time or at a reasonable cost. When one of those dimensions is out of whack, we're going to invent new stuff. And that's what we've done, right? As relational technology has become more and more cost inefficient to operate at scale, we've developed new technologies, new database technologies that actually are efficient to operate at scale. And what happens whenever you develop a new technology to solve old problems is people are going to run to this new technology because they hear about these early adopters that had some good success, and they're going to go and try and deploy this technology themselves, and what they find out is it doesn't really work very well for them. And they're automatically going to assume that they have a use case that doesn't really apply. Something is wrong or something is different about what they're doing, and all these other people, well, it works for them but not me. But the reality is that you just didn't learn how to use the tool. You're trying to use the tool the same way you use the old tool. And if you do that, you're going to have a miserable experience. Okay, so the message here is, if you want to get onto that slope of enlightenment, so to speak, that's really when the skill sets are commoditizing across the industry. When everybody kind of knows how to use it, then it's easy, then the early majority has arrived. Right? If you want to have good results, then learn how to use the new technology before you deploy it, and you'll have much better results. And then nothing is more demonstrative of that than the relational to a de-normalized approach to data modeling. All right? Developers do not like de-normalized data models. It is something that's foreign to our brains. We all love the normal, third normal form, and everyone understands this, but when you get into denormalized data and actually tuning the data to the access pattern, that's a problem that most developers really don't know how to solve yet. I spend a lot of time kind of teaching folks that. So I love to talk to this chart because it really hammers the point home. If you're going to try and use the new technology the way you use the old technology, you're going to have the same results, probably worse. So learn how to use the new technology first. Now, AWS has a ton of new technology for you, right? And a ton of database technology. So this is what I call the hamburger chart. And it's you got the bun on the top and the bottom, and you got the big beef patty in the middle, and a whole bunch of toppings, right? So, but what we're really doing is kind of, again, breaking out the database solutions into the kind of categories of application. If you look at the operational databases, we have our non-relational databases. I don't like saying non-relational because all data actually does have some relationship, or I wouldn't really care about it, right? Even in NoSQL technology, I'm aggregating data somehow, either within the document or within item partitions or whatnot. So I like to say it's more of a denormalized data store, or NoSQL. And then there's the relational databases. Now, relational databases, again, they kind of play both sides. There's no reason I can't build an OLTP application on a relational database. They did it for decades. Why would it not be something I can do today? Well, there's reasons I might not want to do that, and they're related to, well, scale, right? I mean, relational databases don't scale so well. So maybe if I'm building a scaled out OLTP application and I need low latency, then a relational database isn't the right solution for me. But that doesn't mean that it can't do OLTP, right? So there's no category of workload that any database cannot do. It's just that some are better at certain workloads than others, and that's why we have these purpose-built solutions, right? So in the non-relational realm, or in the NoSQL realm, we've got DynamoDB. That is basically a wide column or document store that provides a key value access pattern. We've got Elasticache, which is a pure indexed key value store. We have Neptune, which is a new service. It's a graph database. And we're going to talk a little bit about the differences between these different types of NoSQL, specifically between a wide column key value store like DynamoDB and a graph database like Neptune. What's the use case here, and why can't I just use one for both? And when would I use one or the other? We're really going to get into that. And we'll talk a little bit about some of the others as well. But I'm not going to get too much into the relational stuff because, we all understand relational technology. But we want to talk about the services we have to offer. So the first service we'll talk about is Amazon RDS. And we have hundreds of thousands of users using RDS. Customers using RDS for just about every workload you can imagine. It's a fully managed relational database service. We have 5 flavors of common SQL technology out there. We have our own flavor of relational database management system, which is Amazon Aurora. It's highly scalable, very easy to administer, and for anybody who's ever run production databases, you can start to get really bogged down in administrating the hardware, right? Especially for large, farms of database servers, and maintaining the hardware, maintaining the software, dealing with hardware failures, rebuilding drives. I mean, this is a lot of overhead. So a lot of customers just come to us and just say, look, I don't want to be in the business of managing my relational database anymore. I want you to take care of that for me, and that's what RDS really does. It's easy to administrate and highly flexible. You can scale the database up and down with a couple clicks of the mouse. Typically, if I deploy a relational database in my own managed data center, right, I'm going to want to run that hardware for the life of the hardware. Well, what happens if a year from now I need more horsepower and I've just invested $500,000, right, in a dedicated piece of hardware to run my SQL server? And I've actually seen that happen. I was working with a customer in a previous life, and that's exactly what they did. They spent $500,000 on a piece of big iron infrastructure to run MS SQL server, and 9 months later they had Microsoft in there tuning and tuning and tuning, and the eventual answer was you just need a bigger box. And the customer said, okay, enough of that. I got to go someplace where I don't have to make these big, heavy investments in capital infrastructure that are obsolete within months, right? I want to be in a more flexible environment. So they started looking at AWS and they moved into RDS. They're much happier. I mean, RDS offers instances up to 64 virtual CPUs, up to half a terabyte of RAM. It's really a potent system, multi-AZ deployments, dual SSD, backed storage for high performance. It really does provide just about anything that you would be able to provide with your own managed infrastructure. Getting into DynamoDB, we're talking more about NoSQL here, obviously. This is, again, it's a key value NoSQL database that supports both document and wide column data structures. For those who aren't familiar, you can think of a document attribute would be kind of a JSON structure, right? You just put it into the item and you associate a partition key attribute to that, and then you can pull out that document. A wide column is just simply a bunch of attributes tacked on to the item itself, so that vary from item to item. DynamoDB is fast and consistent at any scale. Like we talked about how NoSQL databases scale horizontally. I'm always going to provide some sort of a key condition that's going to drive me to the exact place in the database that I know exactly what storage node to go read from, no matter how big the database is. It could be a petabyte. And we have tables that are hundreds of terabytes that do millions of transactions per second, right? DynamoDB is, drove Prime Day for Amazon, which is, I think in Sean's presentation we showed over 12 or 13 million requests per second across. That was just Amazon tables, right? That wasn't even just the entire backplane of DynamoDB. DynamoDB was on Prime Day was doing 3 or 4 times that in total requests per second on the backplane. So, and not only that, but if you want to get some idea of the scale of Dynamo, it wasn't even just 2 months later I was in an ops meeting with the GM of DynamoDB and what we call the CDO, which is our commercial, digital, and other development teams, and we were talking about Cyber Monday and Black Friday, and to kind of ease the conscience of one of our largest customers, which is our internal CDO, the GM of DynamoDB let them know, oh, by the way, we're now exceeding what we were doing on Prime Day every day. And that was just 2 months later. Okay, so a year later, I don't even know what we're doing. We're probably doing twice what we were doing, or even 3 times. I don't know what the current numbers are, but just to give you some idea how fast this service is scaling, it's really amazing, what it's doing. So again, fully managed, nothing you need to do except turn it on, and again, dynamic, so it can adapt to your workload. We actually have an auto-scaling function, so it does it automatically. As the load will increase against your table or demand increase against your table, auto-scaling will provision capacity and deprovision capacity as that load expires. So when you look at, and we're going to get into a little bit more about the schema here, because a lot of people, again, we all understand relational technology. It's all pretty straightforward stuff for us. But understanding non-relational is a little different. So, and we do need to understand how this stuff works to an extent to kind of determine whether it's the right database for me, for my workload. So DynamoDB schema, basically, just like all databases, has tables. Tables have items. In NoSQL and DynamoDB, items have attributes. Now, not all items have to have the same attributes, but all items must have one attribute. They must have that partition key, right? Because that tells me where to put the data. If I don't have a partition key, I don't know what to do with this item. So if I don't include that, then you're going to, anytime I insert a document without that, it's just going to throw an error and say you must give me the partition key. So once you do that, then you can provide an optional sort key. And if we give you a sort key, if you give me a sort key, now I can do all kinds of cool things with the items that are located within that logical partition. So you can think of the partition key defining a bucket, right, or a folder, and the sort key defining the order of the items that are within that bucket or the folder. Now against that sort key, I can execute range operators that will allow me to do, selective queries and aggregate the items within those individual logical partitions, right? So it's a nice way to be able to put, let's say, orders by customer, and I want the orders for the customer within the last 24 days or 30 days, right? I could do that kind of query where the partition key might be my customer ID and the sort key might be the timestamp of the order, right? And then I can give a date range query against that sort key and say, for this customer, I want all orders within the last 30 days. And then that would limit the result set that comes back. Now I can provide conditions against the sort key, and that'll give me a nice selective read, and then I can provide conditions against any of the extended attributes, and then that'll filter the result set after the read. Okay? So a nice way to be able to manipulate the results that are coming back when you query. So it's not just a pure key value system. It actually gives you the ability to execute complex queries against the items that are located or stored within logical partitions, right? So how does that really play when we start looking at relational technology? You know, traditionally, again, this has been our approach to database design, the third normal form. I guarantee you, probably almost anyone in this room, I could give you a business problem and you can come back to me within 15 minutes with a nice high-level third normal form diagram of a schema that will support that business problem, right? In this particular case, we're looking at a product catalog. I've got products, and I've got books, albums, and videos, and you can see I have just about every kind of relationship you might see in a normalized store. One-to-one between products and books, one-to-many between albums and tracks, and many-to-many between videos and actors, right? And you can imagine how many queries and what kinds of queries I'd have to execute to be able to pull the data back out of this store, right? Oh boy, there's 3 or 4 different queries with complex joins through multiple tables. This is not going to be an easy operation. It's going to be very CPU intensive. And this is the problem with relational, right? But it was designed this way for a reason. It was built this way because 30 or 40 years ago, the most expensive resource in the data center was disk, all right? And deduplicating the data on the disk was the #1 mission of this database, of the relational database. And it was a powerful tool to do that. In 1983, I went to Macworld, and I remember walking through this, you know, here at Moscone Center, and seeing in the middle of the floor a truck transmission, what looked like a truck transmission. And I walked out there, why is there a truck transmission in the middle of the floor? Maybe it's too big and they couldn't move it. It turned out it wasn't a truck transmission, it was a cross-section hard drive from 1974. It was cool, one of the coolest things I've ever seen. But the most shocking thing was the price tag. They had a price tag on it, MSRP $265,000. And it was 4 megabytes. All right, so just to give you some sense of why did we want to deduplicate the data? Well, because data sprawl has been a problem for, you know, since the first machine-readable punch card was invented in 1880, right? So, you know, being able to deduplicate the data on disk was a very powerful tool, and they did it at the cost of the CPU because the CPU was a fixed asset, right? Hey, the CPU spun whether I was using it or not, right? So let's go ahead and deduplicate the data because that's where I'm spending the money. Well, fast forward 30 or 40 years and the opposite is true, right? Now storage is cheap, CPU is expensive. I pay for CPU seconds, right? I don't want to be investing in technology that is minimizing the most expensive, that is maximizing the most expensive resource in the data center, right? And minimizing the least. So you can start to get the idea here with relational database, man, that's a cost factor that really comes down to scale. Relational databases, great flexibility, not the best from a cost profile, right? So let's talk about how we do that in a normalized store. It's a little bit different. We're going to take those relational hierarchies, right? You can look at kind of that table, you can almost see it. The biggest, the top level item is a product. There's all just different types of products. So we'll build hierarchies that describe our products, and we're going to stick these items into our partitions, either as documents or as items that are aggregated within these product partitions. And now when I go to my database to get the products, I have one query, select star from products. That's a much easier query, right? So this is why non-relational databases or NoSQL databases like DynamoDB scale really very, very well, but can you imagine if, let's say, I wanted to actually start to rotate that data into a different view, right? Ooh, maybe not so, there's no ad hoc query here, right? So I'm going to get the products, select star from products. I'll get the way my products look, but if I want to join these products and start to manipulate these things and create ad hoc aggregations, then that could be problematic, right? So I'm trading off flexibility, but I'm gaining scale and efficiency. So there's always trade-offs here, right, when we start to look at database technology. Okay, the next database we're going to talk about is Neptune. This is a graph database, and it's also categorized as a NoSQL database. Neptune is awesome. It is really about querying relationships. When we talk about relationships, the fundamental thing to understand with a graph database is that relationships are first-class entities in a graph database, unlike any other database. What does that mean? Well, it means really that relationships have properties, right? In a relational database, relationships don't have properties. They just indicate that two things are connected. But in a graph database, I can actually assign properties and characteristics to the relationship between the entities, which means now I can index the relationships. I can query the relationships just like any top-level entity in the system. And this opens up a whole new array of use cases, and we'll talk about some of those. But first, let's get into the architecture and what it's really built for. And what's interesting about graph databases and graph applications and problems is that everything is a graph problem, because all applications are really about aggregations, and aggregations are relationships. So you can really describe just about any application as a graph problem, right? And it doesn't matter what it is, social networking, fraud detection, it doesn't matter. ITSM is a beautiful example. In a former life, I used to do a lot of ITSM software, and we ended up representing IT infrastructure as a graph. And we actually built an event correlation and state engine on top of a graph structure. Then we would just process an event stream against this graph and propagate state through the graph using the edges of the graph that described how to interpret the events and the states of the nodes. It was really a beautiful system. But when you get into graph, there's a couple of things we need to look at as far as Amazon's, or as Neptune's architecture. It has open APIs. It supports Tinkerpop, Sparkle. It's an open framework for traversing the graph, so to speak. We'll talk a little bit about what that means. And it's highly scalable, right? Multiple read replicas. It's multi-AZ by default. And it's cloud-native storage engine. Okay, so you're going to have, Neptune also gives you the ability to provide ACID consistency, which is something that DynamoDB does not. Okay, so what kind of use cases are good for graph? Probably the first one I'd talk about would be, a good way to kind of frame this would be people, places, and things. Right? People, places, and things have lots of different types of relationships, and there's lots of different applications I might build around this. One of them might be a replication, or a recommendation engine. Okay, so in this, we'll take this example of, Bob has some interest in the Mona Lisa, and he wants to go to Paris to see the Mona Lisa, and he would like to go visit things that his friends, right, have potentially gone and seen and enjoyed. So how would I build a schema to support that? And let's walk through the various options we have to do this and decide which database might be the right one for this purpose. So the first one we're going to look at is relational approach. All right, there's a normalized graph design. I actually walked in and dealt with teams that have something very similar to this. And you can think about this as you got this big mapping table right in the middle, and you got all these things that are related to each other, peoples, places, and things. And so let's think about what I might have to do if I were to say, well, let me go get all the friends of Bob that have been to Paris, right? Because I know that's where the Mona Lisa is, okay? Well, gee, that's not easy. I'm going to have to join the people table back to the people table just to find the people who are related to each other as friends. Then I get to iterate through that list of results. Then I get to go find for each one of those things all the places that those people have been and anyone who's been to Paris. Okay, once I've eliminated all those things, then I can go and select all the places that they've actually been, all the things that they've done, right? Again, iterate, 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 traverse, go back, go back. That's not a great pattern, right? Even for the simplest of graph aggregations here, I'm going to have to do multiple, lookups against the database. Okay, so maybe a normalized approach to graph is not going to really be good for us here. So maybe let's take a de-normalized approach to graph. So a de-normalized approach, and I can do this with a NoSQL database. I can do this with a relational database, right? A relational database, what I do is I just create a big table. I start inserting edges. I create a couple inverted indexes on the nodes, on the relationships, on the endpoints. I can do all kinds of cool queries here. What we're really trying to do in a denormalized approach is define some logical partitions that define nodes. And then we're going to push edges into those nodes, all right? So if I want to query the edges for a node, no problem. Select the node itself and all the edges that belong to it. Okay, that's a pretty straightforward query. That's great. I can get all the edges that are connected to Bob and find out things he's interested in. If I want to get the types of people, maybe friends of Bob, I want to get the types of nodes or the types of endpoints that are being connected, I can provide a couple of inverted indexes on those two properties. Right? I can index the relationships and the endpoints, and I can query those things. So kind of getting these first-order traversals or these simple aggregations isn't so hard. Right? We can do this with a denormalized data structure, and I can do this on a relational platform. I could do this on a NoSQL platform. I could certainly do this on a graph platform, right? So if all I need is these kinds of simple traversals, well, I got plenty of options, right? These kind of simple graph aggregations, but the next case gets complicated, right? The one we talked about. Bob wants to go see the Mona Lisa. The Mona Lisa is in Paris. Who does Bob know that's been to Paris? What are all the things that those people have seen? So that Bob can go off and see those things too when he's in Paris. All right, now all of a sudden we break down, right? I'm going to have to traverse this graph. I'm going to have to go and say, okay, who are Bob's friends? Where's the Mona Lisa? Where does the Mona Lisa exist? Okay, it exists here. Let me go get all the people who are friends of Bob who've been there. Okay, now I can go get all the things that those people have seen and all the places that they've been in that location. So multiple trips back, right? So you got to follow the edges to traverse the graph, right? This is actually what graph databases are really, really good at. Why? Because they have an open API, and I can just feed some information about what type of aggregation I want to produce, and they're going to traverse behind that API and serve up a result set. So I call the database one time, and I get the aggregation I need. I don't have to get a result set, iterate through it, and traverse manually, right? So this is where graph databases excel, right? So what we've got here is we've got three types of graph queries. We've got a node query, right? Where I just want to give me the edges for a node. And you could say that's kind of query the primary table, or query an index on the node property. I've got an edge query, right? And that edge query is going to give me the relationships and what are the relationships between the entities. Again, I can just do that with a simple inverted index. So I can solve that those first two access patterns very efficiently with a relational database, a NoSQL database, or a graph database. When you get into the third type of query, now we're talking about hybrid queries or traversal. I can do this with a relational database, but maybe it's not the right purpose, right? Maybe that relational database is going to be a little bit more expensive to try and do these types of queries. So if I have to do these types of traversals, complex, multi-dimensional aggregations, hey, graph database is an excellent way to go. Now, I might be able to, if this is an OLTP app, again, well-known access pattern, I might be able to leverage a NoSQL database and do this by basically projecting those graph queries back into the edges, right? If I know that this recommendation engine is designed to produce that exact result, then I can use something like EMR, or I can even maybe use Lambda, and as I insert edges into my de-normalized graph on a non-relational or NoSQL database, I can then write back the projection so I can serve those result sets up, right? That could be cool if I need something that's going to scale massively, because again, Neptune is great for ad hoc queries and great for these ad hoc graph traversals, but we've got a dimensional factor here that we got to be concerned with. It's the scale factor. There is a limit to what Neptune can do, right? All right. The next couple of databases we'll talk to, again, getting back into kind of that relational sphere, so to speak. Redshift, this is a pretty straightforward data warehousing solution. Important to know, this is available to you. It's a very, very popular service. Again, one of our more popular services, and because it's so inexpensive compared to a dedicated data warehouse service that you might put up and stand up in your own infrastructure, right? And the reason why is because data warehouses really run to support decision support systems, generally speaking. Not many data warehouses are running 100% capacity, full-time, 7/24, 365. Typically, they're batch process type applications or regularly scheduled applications that run against these things. They're daily jobs, weekly jobs, monthly jobs. And with Redshift, I can scale the processing power of the cluster up when I need it and down when I don't. And so I pay for the data storage, but I don't have to pay for the compute 100% of the time. And that drives costs to the floor, right? So when people start to look at Redshift and you look at the TCO of a comparison between a Redshift deployment and maybe standing up this infrastructure and owning it yourself, not only can I roll out a petabyte data warehouse at the click of a button and have it available to me within seconds or minutes, which is impossible, right, in the enterprise IT infrastructure environment. But I can scale it up and scale it down dynamically, and that is certainly something that is not achievable with self-managed infrastructure. So huge advantage for you there. For unstructured or semi-structured data that we can put up there in S3, we can use Athena. Athena is basically managed EMR on demand. You can run queries against your semi-structured data up there in S3 with using ANSI SQL. It's fully open. Interface, you pay for the query. It's fully serverless. Don't have to deploy any infrastructure. It's really, really neat service for running those batch ETL jobs, for doing long-running DSS workloads against large data lakes that you have deployed up in S3. So getting down to the root of things, what we've got is a couple of categories, so to speak, of database, right? We have SQL databases, we have NoSQL databases. Within NoSQL database, we have this thing called graph, and I'll put it in its own category because graph has some very unique use cases. And this is kind of how things break down, right? SQL databases leverage normalized relational or dimensional schema for data warehousing, right? They support ad hoc queries and aggregations, things when I don't understand the access pattern. Boy, an SQL database is something I'm really going to have to look at. So if it's a BI analytics, an OLAP style workload, or some other application where I really don't get, or I really cannot quantify or define up front how I'm accessing the data, your best bet is to try and leverage an SQL solution. NoSQL is optimized for compute, right? It's about OLTP at scale, DSS at scale. You can certainly put EMR on top of DynamoDB, right? You can grind down data that way. It might not be the most efficient way to do things. I might want to actually go with an Athena implementation to do that, but there's nothing that stops you from doing that. They scale horizontally. Again, built for OLTP at scale. And you're designing your schema to represent those instantiated views and drive those computed aggregations, right? You're not going to be able to deliver ad hoc aggregations, but with DynamoDB, you can certainly compute aggregations and write that data back into metadata on the table. So if I need a sum or a count or an average, I can just maintain that as a running aggregation. These things might not be the most consistent view of your data. So maybe I want to look at if I need consistency, I want something that supports the ad hoc queries, ACID consistency and whatnot. And then there's a graph database that's really optimized for querying entity relationships, right? And it's designed to excel at graph traversals, right? So we talked a lot about the characteristics of the workload, and we talked about the iron triangle of data. Well, there's an iron triangle of purpose, right, that we got to go through here. And it's the pi theorem, right? So at AWS, you can have your pie and you can eat it too. But it's basically, there's three dimensions of the workload. Okay, the first we're going to talk about is pattern flexibility. Again, ad hoc queries. Do I need to support those ad hoc queries and random access patterns, or do I have a workload that has a well-defined access pattern, something that is, I can identify up front? It's really the difference between OLTP and OLAP style applications. There's infinite scale. Does the database need to scale without reasonable limits in both throughput and size, right? So if we need to support that kind of infinite scale, that's another dimension that we have on the application. And then there's efficiency, right? How good is the database at delivering the performance that I need for the workload at any given time, right? And again, it's about pick two, because you're not going to get all three. But Amazon has an amazing array of solutions for you, no matter what the dimensions of your workload are, okay? And that's what it comes down to, right? If I need pattern flexibility and infinite scale, we're really talking about data warehousing or DSS, okay? And that's going to be Amazon Redshift and Athena. If I need infinite scale and efficiency, then we're kind of starting to get into OLTP at scale, right? Because those are, and we're going to be looking at DynamoDB. And if I need pattern flexibility and efficiency, then what I'm talking about is BI analytics and OLAP style workloads. I need random access patterns, and I need to be able to support those with low latency. Then I'm going to want to go after relational. Again, as I look at every one of the angles on this triangle, there's a dimension that is not going to get addressed no matter what solution that I pick. And so it's about categorizing the workload, understanding what is the purpose of your workload, and identifying the right solution and the right purpose-built database solution for that workload. All right, so I'm going to leave you with a couple of, we always like to talk about customers. Bottom line is hundreds of thousands of people and customers are using DynamoDB for just about every workload you can imagine. You are all users of DynamoDB indirectly. And the applications, again, Lyft, Netflix, you can all look across just this short logo chart and see there's applications you're all using. When you couple that with RDS and Redshift and whatnot, there's hundreds of thousands more people that are using these solutions. So it's tried and true, right? There's nothing that we're doing here that is experimental. Many, many, many customers have deployed this stuff. They're using it in production of the most mission-critical applications out there. So, why not you? And it's really about purpose-built database solutions that are fully managed, that give you, the infrastructure and alleviate you from having to worry about all these things that would normally be associated with managing your own services, right? The capacity planning, the provisioning, dealing with hardware failures and upgrades, OS patching and maintenance, all the software, right? Configuration, patching, and maintenance. Things that you don't have to worry about when you go with AWS, and not only that, but doing it with basically zero unplanned downtime, and in some cases, like DynamoDB, zero downtime. This is just something that's not easily achievable by even the most mature IT organizations. So, that's, generally speaking, that's what I got for you. I hope that you got something out of today's conversation. If you please fill out your summaries, they're in the app right there. The instructions out there. If you like the session, it's DAT307. If you didn't like the session, it's not in there. All right, thank you very much.